Good morning everybody. Myself Professor Pushpa N. Avanti. So today I am going to teach an optical instrument topic, that is the derivation of the least confusion. See dear students, as you know the optical instruments in a previous video. So but in today's class we shall discuss about the derivation of Fr minus Fb is equals to omega F, that's the circle of least confusion, and derivation d is equals to d equals to 1 by 2 d 1 by 2 d omega. So before going to start the derivation of the least confusion, now we have to discuss some basic definitions regarding this derivation, that is the aberration. As we know in earlier videos, aberration is nothing but it is the property of a optical system such as lenses that results in a light being spread out over some region of space rather than being focused at a point. Means the lens, the images or the light cannot be, it will be focused or it will be merged at a point. It will be spread over the region, and the such a defects of the lens is called as the aberration. In the case of aberration, here we have to see about the spherical aberration. Spherical aberration is nothing but a rays of light from a point on the optic axis of a spherical lens do not all meet at the same image point. The rays passing closer to the center are focused farther away than the rays passing through a circular zone near its rim. A circular cross section is formed whenever a plane held perpendicular to the optic axis, it will be made to intersect a cone. So the area of cross section varies with the distance along the optic axis. Therefore, the smallest size is known as the circle of least confusion. So here the most spherical aberration free image is found at this distance. Means here the distance in between the two rays, there will be a distance, there will be a space in which the object, the image of the object will be formed, and that distance is called as the least or the circle of the least confusion. So here now we have to discuss about the longitudinal and lateral chromatic aberration. So the lateral chromatic aberration or the longitudinal aberration is nothing but the failure or the defects of the lens to focus all colors in the same plane is known as the chromatic aberration. Chromatic is nothing but it is the failure of the lens or the defects of the lens to focus all colors in the same plane. So the lens which does not having this property means the all colors, actually the all colors will be emerging, it will be merging at a point or it will be meeting at a certain point. But in the case of the aberration, the lens, it will be focus all colors in the same plane, means it doesn't focus all colors in the same plane is known as the chromatic aberration. So the refractive index for red is least at the red end of the spectrum, hence the focal length of the lens in air will be greater for red and green than it would be for blue and violet. Chromatic aberration affects magnification along the optic axis and the axis perpendicular to it. Therefore, the earlier one is known as the longitudinal chromatic and the later one is known as the lateral chromatic aberration. See, this is the figure. So you will get the clear idea about the aberration. See, this is the object and this is the lens. When the object is illuminated with the white light, so when light is passed through this lens, after actually if this lens is not in a defect or it is not at all any defects in this lens, all colors will be meeting at this point only. But in this case, what will happen here? The lens is having a defects, means here all the rays which will be coming from this white light, it will be split up into number of constituent colors. So here the blue will be merges at this point and all the red rays will be merges at this point. Therefore, the different colors will be merges at different points. So here we have to consider red and blue rays. So the blue is near to the lens and red is further to the lens. Therefore, in between the blue and red, there will be a object of the image will be formed, and this distance is known as the least circle of least confusion, circle of least confusion, and also this is known as the chromatic aberration. So in the case, now we have to derive the main theme of the today's content, that is the derivation of the FR minus FB is equals to omega F, that is circle of least confusion. In the case of this derivation, here we have to take longitudinal or axial chromatic aberration. See, when a parallel beam of white light is passed through a lens, see, now we have to see this figure. When a parallel beam of white light, it will be passed through a lens, blue rays are brought to focus at a point near the lens and the red rays are brought to focus at a point away from the lens. And other color, or it will be other color foci are formed in between blue and red rays. So the image spread over this distance, over a distance x from blue focus to red focus, and this distance is taken as x. So that is x is equals to FR minus FB, and this FR minus FB, the difference between the focal length of the red and blue rays is known as the longitudinal or axial chromatic aberration. Therefore, an equation for axial chromatic aberration is derived as follows. The focal length of the lens is given by, that is 1 by, that's F1 is equals to mu minus 1 into 1 by R1 minus 1 by R2. This is the lens focal formula, that's the focal length of the lens. Mu is nothing but it is the refractive index of the lens. R1 and R2 are the radii of the curvature. So now we have to take 1 by R1 minus 1 by R2 is equals to, also simplifying or rearranging the terms of the equation 1. So then we will get 1 by R1 minus 1 by R2 is equals to 1 by F mu into mu minus 1. Similarly, we have to, so this is for the general expression. Now we have to apply this equation for the red as well as the blue rays. For the blue, it can be written as mu b minus 1 divided by 1 by F mu minus 1. And call this equation as 3. And for the red rays, the focal length of the red rays is given by mu r minus 1 divided by f into mu minus 1. Call this equation as 4. So now we have to subtracting equation 4 from equation 3. Then we will get 1 by fb minus 1 by fr is equals to mu b minus mu r divided by f into mu minus 1. See here, mu b minus mu r divided by mu minus 1 is nothing but dispersive power of the prism. Dispersive power of the prism is nothing but it is the ratio of the angular dispersion to the mean deviation. Therefore, here we have to take a mu b minus mu r divided by mu minus 1. Or so now we have to, and also we have to take in fr into fb is equals to f square. After simplifying this equation, fr minus fb divided by fb into fr, it is equals to omega into f. Therefore, fr minus fb is equals to omega into f. So in this equation 6, in equation 6, this omega is nothing but it is the dispersive power of the material of the lens, and f is nothing but it is the focal length of the mean ray. Therefore, axial chromatic aberration is equals to the product of the dispersive power of the material of the lens and the focal length of the lens. See, as omega as well as the dispersive power of the lens and the focal length of the lens are constant, a single lens cannot be used to minimize axial chromatic aberration. So, if we have to reduce the chromatic aberration, axial chromatic aberration, so as concave lens forms virtual focus, the focal length of the lens for mean ray is negative, and hence the suitable combination of convex and concave lens can be minimized axial chromatic aberration. So keep it in your mind, the single lens cannot be minimized the chromatic aberration, but we have to combine the suitable combination of convex and concave lens, then only the lens can be minimized the axial chromatic aberration. So now come to the circle of least confusion, or a measure of lateral chromatic aberration. See, now we have to consider this figure. A point object, that is O, it is illuminated by the white light, is situated on the axis at a distance from the lens, and the blue and red images are formed at the positions P and Q. So these are the images. At this point, at the point P, blue images are formed, and at the point Q, images of the red rays are formed. So, and here a screen placed at AB. So here now we have to place the screen, that is AB here, has an image with least lateral chromatic aberration. So here the diameter of the circle of the least confusion, which gives the measure of the lateral chromatic aberration. So now we have to calculate the lateral chromatic aberration. Let U be the object distance. Object distance is nothing but it is the distance from the object and the lens. And here VR and VB. VR is nothing but it is the image distance for the red, and also VB is nothing but it is the image distance for the blue. And if FR and FB are the focal length of the red ray and blue rays of the light. So according to this, then 1 by VB minus 1 by U is equals to focal length of the, according to the expression for the focal length. So now we have to take in here for the blue ray. So then 1 by FB with the focal length of the blue ray is equals to 1 by VB minus 1 by U, or for red ray we can write it as 1 by VR minus 1 by U is equals to 1 by FR. So now we have to subtracting equation 2 from equation 1. After subtracting this, we have to get VR minus VB divided by VR into VB, then FR minus FB divided by FR into FB. But now we have to taking the terms VR into VB is equals to V square, FR into FB is equals to F square. Therefore, VR minus VB by V square, FR minus FB by F square. So, as we know that FR minus FB and VR minus VB is equals to V square, then it becomes omega F divided by F square. See, omega F, that is VR minus VB equals to V square, FR minus FB by F square is equals to omega F by F square. Then it becomes simply omega by F, because we know that FR minus FB is equals to omega into F. See, this is the value of the FR minus FB is nothing but omega into F. So, omega by F. Therefore, VR minus VB is equals to omega V square by F. Now we have to consider from the similar triangles LQN and AQB. So this is LQN, that is LQN, and also the AQB. AQB is nothing but here AQB. LQN and AQB. Therefore, CQ by AB is equals to MQ by LN. And also for the similar triangles LPN. See, for blue rays LPN, and also ABP, that is ABP. LQN, APB, sorry, LQN and APB. And CQ by AB is equals to MP by LN. And now we have to adding both these equations in 4 and 5. We will get MQ plus MP by LN. But PQ equals to VR minus VB. See here, P and Q. PQ is nothing but here. This is the for blue and this is for red. Image of the blue ray will be formed at this point. Image of the red ray will be formed at this point. Therefore, VB and VR we can take it as VR minus VB. And AB is nothing but it is the diameter. It can be taken as D. So in the that is D is nothing but diameter of the least confusion, circle of the least confusion, and Ln equals to D. Consider this one as Ln. This Ln is equals to D. Ln is nothing but it is the diameter of the lens aperture and it can be taken approximately. Therefore, MQ plus MP is equals to VR plus VB. MQ is nothing but this is the MQ is nothing but image of the red ray, and MP is nothing but image of the blue ray. Therefore, VR minus VB divided by D is equals to, so MQ plus MP is equals to VR plus VB is equals to 2V. Now we have to substituting these values in equation 6, MQ, MP and Ln value. Then we will get VR minus VB divided by D is equals to 2V by D. Then make it D is equals to D into VR minus VB divided by 2V. So now we have to using equation 3. So then we can rewrite this one as rearrange the terms. Then D is equals to 1 by 2V omega V square by F, or 1 by 2 D omega V by F. For a parallel beam of instant light, then equation it will be reduced as the form D is equals to 1 by 2 D omega F by F, or we can take simply 1 by 2 D into omega. Therefore, thus the lateral chromatic aberration depends on the diameter of the lens aperture and the dispersive power of the material, but it is independent of the focal length of the